Okay, good morning. Welcome back. Happy Wednesday. Today we are doing our third and final day on geometry stuff, a little bit on volume, a little bit on arc length. That'll be brand new, this arc length thing. Hopefully you're working on project number 5. That's going to be due the Monday when we come back from spring break. Questions on the calendar? Okay. So here we are on page 47. I want to make an announcement just to make sure that something is really clear because it actually wasn't written out in this detail in the project assignment that you're working on. But for the Candies project, you are not just going to write an integral. You are going to do exactly what we've done the last couple of classes where we end up finding the area of a slice and then we put a sigma in front of it, and then we put a limit in front of that, and then after we've got all that laid out, we write our integral down, okay? So make sure that you put all of this stuff in the project for each of those 4 Candy questions. Maybe even make a note on the project directions that it should follow this format. Don't forget the I's. Delta X or delta Y will depend on how you draw your pictures. This is written clearly in the project, but I'm just going to say it so that you hear it. There are 4 candies, and you're going to find the volume of each of those 4 things. And in the directions, it says you're going to use the method of discs for 2 of them. That's what we covered last class. And then you're going to use the method of shells for 2 of them. That's what we're covering right now. All right. You get to pick. It hardly matters which ones you use, which ones on. I just want you to practice 2 of each, but make sure you don't just do all 4 with shells. Got to do, or all 4 with discs. Got to use this method too. All right, I think that is good. Also want to be clear in one of the steps, anybody have the project assignment handy right now, this one? So in step number 4, it says evaluate the integral for the volume. You may use your calculator here. I want to be explicit. I don't need you to do any antiderivatives on this project. You are just typing an integral into your TI-83 or into Mathematica or into Wolfram Alpha, just writing down the output, okay? The hard work is this setup here. So I want to make the integral part easy for you once you've got it written down. Everybody clear on that?
Our measuring of the candies.
Yeah.
How precise?
As precise as you can, but you know, like there's a wide range of right answers for me. Yeah. Nice. Micrometers. Awesome. Awesome. Nice.
So if we the e to the power, do you want us to leave it in that form, or do you want like a decimal?
Whatever your calculator gives you is probably going to be a decimal. Yeah, totally fine. All right, any other questions there? Okay. All right, so that's good. And one last thing about projects. I just handed back the Gamma project. I think the Gamma project is one of the harder ones from this semester, and you guys did awesome. So I just wanted to say good work. Like it's tough stuff, and it went really well. Yeah. Caitlin gave you 2. Yeah, okay. So daily summaries. Today we study another technique for finding volumes of revolution called the cylindrical shells method. In this technique, our slices are parallel rather than perpendicular to the axis of revolution. We're going to skip some of this text here and jump down to number 2, which says, let's have a look at this animation here. Let's have a look. Right here. Okay, so in this setup, we've got this red region right here, and we are going to spin it around this vertical dotted line right there. Okay, and so we got this thing. This is one really fat slice, that rectangle, and it's going to swing around over here like it's going to come out of the board and then go behind the board and then swing back around. All right, so we can kind of picture this rectangle swinging around. You could call that shape a washer, but that's not really a great name for it. We're going to call that thing a cylindrical shell. I'll actually spin the thing right here so we can really get a good look at it. So behind the board, and then in front of the board, and then back, okay? Cylindrical shell. It's a cylinder with another cylinder cut out of it. Like I said, I mean, you could call it like a really tall washer, but this is fundamentally a different thing than the washers we were talking about the other day. And so what we're going to do is, just like before, let's see if I can hide all of that. there we are. We're going to, we're just going to build the solid that we're interested in by finding volumes of shapes that are easy to find volumes of. How could we get something better as an approximation for this thing? Just thinner ones. Like instead of using 5 of these cylindrical shells, we use 10 or 1,000,000 or infinity in the limit. Okay. All right. So the question is, how do we calculate the volume? There we go. How do we calculate the volume of one of these cylindrical shells? Now, in reality, if we want the exact volume of that thing, we're going to do the volume of the outer cylinder minus the volume of the inner cylinder. That's not what we want. We want to approximate the volume. We're imagining that this thing is really, really, really thin, right? And so what we're going to do is we're actually going to take a look at just the outer cylinder, say just one of them. We're going to measure its surface area, right? We'll get some number, some square unit number for the surface area of that one cylinder. And then we're going to multiply that surface area by this thickness up here. And that's going to be a pretty good approximation for the actual volume that we have there. Do we see it? So you take the surface area, you multiply by the thickness. It's not going to be perfect because the surface area of the outer cylinder is not exactly the same as the surface area of the inner cylinder, right? But it's going to be close enough, especially as these rectangles get thinner. So the big question is, what is the surface area of a cylinder? For me, I memorize it as circumference of the circle. What's the circumference of the bottom circle? 2 pi r. And then we're going to multiply it by all the other circles that are stacked on top of it. And we'll call that h for height, okay? So the surface area is 2 pi r times the height. And then we're going to multiply that thing by the thickness of the cylindrical shell, all right? Okay, so I think that is that. What's going on here? This is the same idea. So the actual shape that we were interested in finding was this thing, and we approximated it with 5 cylindrical shells, okay? All right, so let's do some calculating. Here is the picture, y equals x cubed minus x between 0 and 1, which are just the x-intercepts here. So we've got that region, and we're going to spin it around the y-axis, okay? And so there's this duplicate thing here, and so you imagine taking it and spinning it around into the other side. So don't draw this because I'm going to erase it in a second, but suppose for a second that we try to use the method from last class. Remember, with washers and discs, the slice is always perpendicular to what you're spinning around. And if we're spinning around the y, that means this is my slice, right? And so if I spin that thing around, is that a disc or a washer? That's a washer, right? And so is this going to be a delta x or a delta y for the thickness? That's a delta y. And I guess I need to know how much x, you know, whatever the big x coordinate is, and then whatever the little x coordinate is, small. I need to like find equations for those things because delta y is the magic letter in this case. It's got to be all y's. Okay, so that means I have to solve my equation for what letter? I'm going to solve it for x because I want to know what the thing is in terms of y. So, for example, pi times x big squared, that's the pi r squared for the outer circle of the washer, but I'm not allowed to have an x there. So I need to put something that is y's. I need to solve that equation for x so that I'm allowed to have y's in here. The problem is that I personally do not know how to solve that equation for x. It is possible to solve it, but I don't know how to do it. And so all of a sudden we get to a place where if we try to use the washer method, we have an algebra block. We can't get past it. Okay, so having a horizontal slice in this case is bad news because it involves solving an equation for x that I can't. So let's try a vertical slice instead. Do write this part down. So we've got our vertical slice there, a little rectangle. And we're going to take that thing and spin it around the y-axis. So maybe draw the same little rectangle on the other side. And I got one circle here and one circle there. So that is our cylindrical shell, really thin cylinder, kind of like a paper towel tube. Okay, so the volume of one slice is roughly equal to, we said it was the surface area, which is 2 pi r times the height, multiplied by the thickness. That right there is the only thing that I know about this method. Right? You're going to find some fancy integral formulas in your book. I don't know them. I know this. Okay, so let's label this point right here. This is our generic x comma y. And that's going to allow us to start to rewrite this thing. 2 pi. Okay, the radius. Radius is here to here. What's a good name for that radius? That's x, isn't it? Is that exactly the x at whatever point you're at? We're just calling it x. Okay, so the radius is x. So here to here, x. The height of this shell is here to here. Is that y or is that x? That's y, isn't it? One minor detail, what kind of a number is y? Is negative, and I want my height to be positive. So I guess you could put absolute value. Really what I'm thinking about is that it is y at the top minus y at the bottom. So y at the top is always 0 and y at the bottom, and we'll just call it y for right now. So that's going to take care of making it positive. Thickness. Thickness of this shell. Delta y or delta x? Delta x. Great. Two pi times the radius times the height. That's an area, and then we multiply by the thickness to give us the volume roughly. Okay, what's the magic letter we want everything to be in terms of? X, delta x. Okay, so that means we just need to change this y into something with x's. Do we have an equation for y in terms of x? We do. That's why this kind of slice was better than the horizontal slice that we failed at earlier, is that this is the moment where we can just change the y into the equation that was given. So that means this is equal to 2 pi times x times 0 minus, what's the equation? X cubed minus x delta x. Okay, the hard work is done. We'll spend one step cleaning this up, and then we'll throw it inside of our sigma. So that is equal to 2 pi if you x, 2 pi x. If you distribute the negative sign through, the x becomes positive and the x cubed is negative. So I'm just going to reverse the order here. That's it. Yes. Okay, notice that this does not have anything squared in it. Last class, everything had something squared because it was all circles, right? Circles and washers. No squared here. 2 pi r h, nothing squared. Okay, so now we'll just throw stuff inside of a limit and inside of a volume or a sigma. So the volume of the whole shape is equal to limit n goes to infinity, summation I equals 1 to n, right? This is just cookie cutter. It's always that. What are we putting inside of the sigma? Just that function that we created. That was the hard part. 2 pi x, x minus x cubed, delta x. What's the only thing we need to change when we write that formula? Is just to put i's on the x's. I there, I there, I there. The delta x never gets an I. It's just the width. We're not counting that. And then when we have something written in exactly that form, limit of sigma of function with delta x, how can we rewrite that conveniently? As an integral. That's what we do, integral. So we copy that formula, 2 pi. What's the small change that happens in the formula? So we can get rid of the i's. Feels kind of redundant, like we put them in only to take them out in the very next step. Small change on the delta x dx. And then the only other piece here is those limits of integration. Yeah, so let's look at this picture here. So you've got the region 0 to 1, but then if we've got the duplicate of it, it's really negative 1 to 1. So which is the right thing to integrate? Negative 1 to 1 seems like it'll get us everything, right? Why is it only 0 to 1? That formula, the 2 pi r, that takes care of doing the entire circle. You don't want to, like, if you go negative 1 to 1, you're going to get double the right answer. You are taking this single region that only lives between 0 and 1 and spinning it all around. And the formula takes care of the spinning it all around. So it is just 0 to 1. Okay, so that's it. We're not going to do the integral. It's a really easy integral. Just multiply that x through and it's a polynomial. Quick visualization for this shells thing. This piece of paper does have a volume. It's a very small volume, but it has a volume, but it doesn't, like you can hardly even see the thickness. But if you take enough of these little things together and you wrap them around, and all of a sudden we have something that has some clear volume, right? That's what's going on here. You're just taking lots of little pieces of paper, really, really thin pieces of paper, and just smushing them all together. Okay, one more thing for today is arc length. So here we're just going to give you the punchline. So first of all, it is quite surprising that it actually turns out to be possible to find the arc length, the length along a curve. Like finding lengths of straight lines is easy. Finding lengths around a circle is easy. But any other curve, yeah, I don't know. Like I don't know any other formulas for lengths around a curve, right? But it turns out it's easy. It turns into this integral right here. If you want to find the length of the curve y equals f of x between a certain x equals a and x equals b, it is a matter of doing this integral, square root of 1 plus f prime of x squared between a and b. So that's the punchline. We're going to prove that punchline. You can put your pencils down. You don't need to write any of this. That magic formula up there hopefully will seem less magical in like 2 minutes. It's one of the few formulas that I'm going to ask you to use and not worry about writing down the slice and the summation and the limit, right? All of the magic integrals that we're doing, we're building them. This is one of the few that we're not going to build. We'll build it one time here and then we'll just use it. Okay, so here's what we got. We've got this curve right here. We're looking for the length of this curve between, some far off point here and some far off point here. So we want the actual length there. Like the only tool we might have with estimation would be like put a piece of string there as best you can, line it up, and then straighten it out, and then put it against a ruler, right? So calculus is going to give us an exact answer here. What we're going to do is look at 2 points that are close together. We're calling them x1 and x2. They're really far apart here just so that we can see them. But we're imagining they're very close together. And we are going to approximate the part of the curve, the length along that curve between those 2 points. We're going to approximate that with the only thing that's easy to find the length of, which is a straight line. Would you guys agree that the length of the green is fairly close to the length of the red? And if I picked my points closer together than they are in this blown up picture, then the green would be really close to the length of the red. Okay, so here's the derivation. Again, you don't need to write any of this thing down. We are going to call delta y this vertical change in y, and delta x the horizontal change there. So we've got a right triangle. We're going to use Pythagorean Theorem in a second. One small thing, would you guys agree that the slope of the tangent line, let's say the slope of the tangent line in this point right here, is not too far from the slope of green? They're pretty close together. And again, if my points were really near each other, then the approximation would be better and better and better. So, so if we wanted to, we could say that the slope of the tangent line is roughly equal to, what's the slope of the green in terms of these symbols here? Delta y over delta x, right? That's just like a basic slope of a line. Okay, so they're approximately equal to each other. All right, so we're gonna use that fact. Let's go ahead and multiply both sides of this equation by the delta x. So we get delta x times f prime of x is approximately delta y. Buy it? Okay, so Pythagorean theorem to find the length of that green right there. Let's call that thing c. So that means that c squared equals what? Delta x squared plus delta y squared, right? Okay, so that means that c is just the square root of that stuff, right? Okay, and now we're going to make a substitution. Delta y, we have already seen, is roughly equal to delta x times f prime of x. So I'm just going to put that right in here, all right? So that gives me square root delta x squared plus delta x times f prime of x squared. Fair? This is starting to look like that magic formula that we're building that's at the top. Again, I gave you the punchline. It's starting to get there. Finally, we see an f prime of x squared right here, and that's in the formula. Okay, tiny bit of algebra here. This is equal to square root, that's a delta x squared, plus that square comes in and hits both of these guys. So it's delta x squared times f prime of x squared. Good. Square both factors. And then what can you factor out of the two terms there? Delta x squared. And then you can take that further outside of the square root, and what does it become? Delta x. So we've got delta x times the square root of what's left here when you took out the delta x squared? 1 plus what's left here? F prime of x squared. Good? And that's really looking like the magic formula, isn't it? Yeah. Okay, that right there is approximately equal to the length of the green. That's what we were finding. And the length of the green was just one of many different line segments, like just lots of green line segments to approximate the actual length of the curve. So really we should add up a lot of things that look like that, a lot of things with that form. And then we should take a limit as the number of little line segments goes to infinity. And so this guy right here, when you put inside of a limit and the sigma, so it's limit sigma of that thing turns into what? Integral. Okay, square root 1 plus f prime of x squared. Delta x becomes dx, and you just go from x at the far left to x at the far right, which were defined as a and b. That's it. Not so magical. Okay, so let's actually just see how to use it. Number 7 says find the arc length of y equals cosine of x from x equals 0 to x equals 2 pi. I'm going to draw a picture, but you do not have to have a picture for any of these kinds of problems. So there is 0 to 2 pi on cosine. So what I'm interested in is knowing the arc length, the length of that thing, okay? All right, let's calculate. According to the formula, we better find f prime of x. So let's do that here on the side. What is f prime? Negative sine of x. And so we'll use our magic formula, L equals integral a to b. How much is x at the far left? 0, and at the far right? 2 pi. They're both given to us. The formula always says square root of always 1, always plus, always something squared. What is the something? Negative sine of x. And that's it. If we could somehow find that antiderivative, we've got our arc length. Sadly, arc length formulas are notoriously difficult in terms of finding antiderivatives, so almost all the time we're just going to do it on the calculator. square root 1 plus negative sine of x, that guy, sine of x squared, comma x, comma 0, comma 2 pi. One small thing before I hit enter, what do I need to check on my calculator? Yeah, I need to make sure you're in radians. Anything in calculus is in radians. Okay, so if I got my parentheses right, then this should work and give us our answer. There you go. If you take a stroll along one cycle of the cosine curve, you will walk about 7.64 units. So Andrew is suggesting that if we change this to cosine instead of sine, that it's going to be the same. Is that right? Why is it the same? What's the translation? So what did we just find the length of the second time? We just found the length of what function? That cosine of x is supposed to be f prime, right? If we're using the arc length formula. We just found the length of the sine function. And because it's one period, and you know, like sine and cosine are basically the same, it's the same. Yeah, good. Okay, go ahead and start on the activities on the next page. Real common, we're just going to ask you to use your calculator to do the integral. So it's more important for me to get the setup right.